It'd be better if it moved.
Would be.
Ready? Okay,
Yeah.
I'm ready, I guess.
Okay.
Take it away. Okay, hi everyone, thanks for tuning in. This is my presentation about visualization of coastal data with KML. Okay, my name is Thijs Damsma, and I've done this work for EcoShape last summer, and all the work I've done is available on openearth.eu. Now, first a little bit, this is going to be about data from the Netherlands. That's where I'm from. The Netherlands is a low-lying country, and well, we basically owe our existence to coastal zone management. If we wouldn't have managed our coastal zone, the sea would have taken out at least half of the country. So that's why in the Netherlands, coastal protection is very important. Now, within the Netherlands, we have this new thing, EcoShape, Building with Nature. That's a collaborative research program for integrated coastal zone management. So just a bunch of companies and institutes work together, put up some money, and well, basically do more research about the coast. And of course, Building with Nature indicates that it's all sustainable nowadays, just like everything has to be. Now, within EcoShape, we have a thing called Open Earth Tools, and that's like the geeky part of it, the technicalities to facilitate the research. Of course, when many people do a lot of research, you need some technical infrastructure to help you out. So Open Earth Tools is all about managing data, because basically research, or the research we do, is mostly about managing data. So it's collecting data, getting it from whatever institute owns it, and then we collect it, we store the data, we put it in like manageable formats, we put everything in NetCDF, process the data, so do whatever you want with it, and then present the data to whoever's your audience. So that's the research cycle, so to say. And well, one of the basic things we want to do, we want to collect all the data available, because nowadays in research, it's usually you spend a lot of time collecting your data, finding out who owns it, where is it, how is it stored, which format is it in, and how do I get that into my whatever computer program you use to process it. Also, another thing we do next to collecting and storing data is sharing tools. So it's we don't want to reinvent the wheel every time. So everybody is encouraged to share as much of their programming with other people as possible, so everybody can use and work on each other's tools. And we have a Subversion repository with scripts. A lot of it is in MATLAB, because that's where a lot of coastal researchers are familiar with, but also Python, Fortran, whatever you can put in there. And the participation is, of course, important. More is better. So we have to have like an attractive thing that everybody feels encouraged to sign up on and to work with. Now that's where it gets a bit complicated, because not everyone is a programmer, and if you explain these kind of sheets with how we manage data, how we process it, how we have different servers to do everything, for a lot of people, especially, let's say, the non-technical, the non-programmers, it's just basically a bunch of digital mumbo-jumbo, and they don't really know what you're talking about and what you can, or what the advantages are of joining your program. So the important thing is a visualization, and this is a scan of a book, which is every year they bring out a new book which shows some coastal data from the Netherlands. So you have a map, you have some green bars which are good, and you have red bars which are bad. But it's a book, so you have to print a new one every year, and well, it's not interactive, so it's really kind of static thing, and this is how it's done nowadays. And of course we want more things. So another way to present your data is, of course, in computer programs, but you usually get plots like this, or like this, or like this, and you kind of miss the context of what the data means, and it's not always that appealing, so to say. It's kind of ugly. And then, well, it's good for some purposes, but as an attractive way of presenting your results, it's maybe not that good, because it's all very static, and still you don't get user interaction. Or if you do want it, you have to develop a user interface, and those are expensive to develop, and it's difficult to do that in a proper and nice way. So we have another thing, and that's called Google Earth. So we use Google Earth to present our data, and there's sort of like a visual front end for the databases we've created. We're experimenting now how we can use Google Earth to its maximum to interact with the data and to present it. So this is, I want to give you a live demonstration of the Google Earth stuff I've done. So switch to Google Earth, and I'll just pull up a chair. Okay, so first let's go to the Netherlands. So fly here. Netherlands, it's a country right down here. Amsterdam, the capital. Okay, first I'll show you is a data set which we only recently got hold of. It's a Dutch height. It's like a datum of the country. And this is a tiled image I've generated using the tools we have, which show the height of the country. Now I've used a coloring which more or less indicates a natural beach color. So blue is underwater, submerged, and green is above, and sandy is like a sort of beach level. So if I just switch it off, you see that a lot of the country is actually colored blue, which indicates that it's pretty much below sea level. And well, you'd reduce the size of the country by about 50% if there were no sea protection. So just to give you a bit of an idea why we think coastal protection is so important in the Netherlands. So well, the good thing is you can use Google Earth to like present data which you would otherwise also present. But if you look at the resolution of this map, it's actually pretty high. And if you print this out, you have a huge map. And if you're only interested in a little bit, well, then you need a lot of small maps. But that's really inconvenient. So this is a big advantage of Google Earth, is just being able to zoom interactively. It dynamically loads data when it needs to. So you really, you can get a good overview of your data. There's much more possibilities, and this is show you a little thing we've made of Katrina, the hurricane. This is a little animation of the hurricane in which the water levels are indicated by the coloring. So the Gulf of Mexico, and the arrows indicate the wind. So just play this. See how it needs to load a little bit more. Okay, just takes. So okay, it needs a bit time to load the background images. But as I scroll through, get a bit smoother. And you see here all the arrows indicating how the hurricane has developed and how the wind pushed the water. And here you can really see clearly how the wind pushed the water all up to New Orleans. So you can understand why New Orleans was so badly hit, because just before the hurricane reached the shore, the water level setup wasn't that bad. Really, as it progressed closely to the shore, here you see it, it really pushed the water all the way up to the back of the city, and that's why we got so much damage there. So really you can use Google Earth to make simple animations and just loop through them as you go. And if you have a map any other way, of course, it's really hard to get this level of user interaction where you can just scroll through your data just like that. So this is one of the things I'd like to show you. Well, in the Netherlands we have an estuary. It's called the Westerschelde. It's down here in the bottom, and this is the harbor of Antwerp. So there's a lot of shipping from down this corner all up to the sea. That is an estuary that well, you need to do a lot of maintenance to make sure it's deep enough. So there's a lot of maps of it. So first I'll show you like a bathymetric map of this estuary. I'll just change the angle. And well, the good thing of Google Earth is that you can easily compare different data sets if you at least treat them in the same way. So the one I first show you, the height data set of the Netherlands, this is a different source. You see immediately, if I just pop it on and off, that in the estuary you get basically the same data, but it's slightly different. So if you're really interested in it, you could check it out, why is the data different. But at least visually you can get a quick impression why or that there's different data, different sources, that they're not always identical, of course. Now you can use like a traditional quiver plots to plot the flow, because a simulation was done here. So using advanced modeling, a simulation was done of the tidal flows and the speeds of the water which you get. So at a certain time, these arrows represent the flow you have in your estuary. And of course, static arrows, that's something maybe of the past. So you want to have the flow and have the flow dynamically. So let me just load that. Okay, it takes a sec. And now if I loop through it, you get a much better indication of where you have the flow. You see at the deep parts you have redder, bigger arrows moving faster, so that indicates a strong flow. And with the downgoing tide, well, all the water flows back. You can see it really follows the gullies, and gives you a good indication of where the flow is and what the important areas are, and gives you a nice way to disseminate the results of a computational model within the public, in a way that they can actually play with it. Because just push the play button here, but of course you can also drag different time steps, or maybe if you enhance the slider bar, you can get a more or less of a history, let's say a particle tracking kind of a way of how the flow has developed. Now all these computations were done on a certain computational grid. It's also a good thing to load that in Google Earth. And you see here all the black indicates the grid, and these are all grid cells. So it also gives you a good indication of which resolution you can achieve and how this lines up with, for instance, a satellite image. So it lines up pretty good, but not perfectly. So let me, so this is let's say the computational grid which we've used. Now it gives you an idea of the scale and the size of what you could achieve. Now another way of presenting the depth would be, let's say, using a contour plot. So also you use contours here, but as Google Earth is 3D, thought why not make the contour plot in 3D? So this is what I've done. Gives you a nice 3D contour plot, but unfortunately the digital terrain model is not user adjustable, which means that I have to plot something which is underwater, I have to lift it up above the ground, and then exaggerate the height a bit to get an indication of how deep the gullies are. So you can really see the really steep edges here. If I just go down here. Now, I could add some labels here. A good thing about Google Earth is I don't have to worry about all my labels like clogging up, because as I zoom out, it'll draw less labels. So always make each individual label visual. Now also I could combine this with the grid I just showed you, and then you get a nice indication of the 3D grid which is created to do these model runs. So this is basically I think a powerful visualization which you could never achieve, or you can't achieve in any other way, hardly. Now, another data set which I've put in here is called the Dutch beach lines. It gives an indication of dune foot and shoreline positions throughout the years. And I'll just zoom into one of these islands here. And now the data goes back. This is 1842. And as soon as these lines pop up, that's where I have measurement data available. So the blue line indicates, let's say, the shoreline, the edge of the beach, and the green line, the dune foot, so where the beach goes over in the dunes. As I scroll through that, you really get an indication of how this island has changed throughout the years, where it grows, where it erodes. And this can help, let's say, general public understand what's natural variations or what are, let's say, artificial ones, and where you should be worried about or what not. It just really gives a quick view of what you can expect. And also, if you make it broader, the slider bar, you get an idea of the variation. So it's normal that you have let's say, a few meters of variations at points. And if you want to measure, you can just use a ruler tool here and then see how many meters or feet of variations you have throughout a certain time span. So this is really something which can help out a lot. And I've also plotted that the grid over which these lines are measured, just let's say to give an indication. Now, other data sets have also been created. This is called a Yarkus data set. Now, it's only available from 1960 something. Now, here it is. And these are coastal profile measurements of the dunes. Now, normally these are profiles, you would draw them in a plot, but here I thought why not plot them in 3D just over the map, which over the satellite picture, gives you a good idea of how these different data sets, how they are, what context they are made in. Now, in this, a powerful illustration of this is all these lines which you see here, they all seem to represent dune profile. You can see by a line that actually this line is nonsense and that line is nonsense and that one is good. But you can see from the context which you see on this satellite picture. Let me just illustrate this to you. Okay, so here you see dune profiles from year to year. See also how they influence, of course, the profiles influence where the beach is and where not. So you see the blue and green lines moving back and forth. But also you see the lines here on the right side jagging very much from year to year. And I'll just expand the time span on which I'm viewing. And you see here that there are really big variations in the dune profile. And here also, from year to year. And if you just look at the satellite picture, you immediately understand why, because this is not a Joom profile. This is actually a coal stack of some kind of big factory over here. But they are included in the data, and if you don't have the context, there's no way to know, except if you very closely study the data, you ask some questions. But here, you can just easily have a glance at your data, just fly over it, and those things, they become clear pretty quickly what's going on. So the next data sets, the last one I want to show you is called, it's called vakloading, a Dutch word, but it means basically height maps which are measured from year to year at different locations. They're all stored in different charts. And well, if I go to this location, I've taken some metadata from the database which is behind this, and it just gives a really it's a quick way to look at metadata, even though I didn't put very much in here. But you can see the coordinates of the measurements and whatever information you want to show here. You can see the years of which is measured. And on a few years, I've pre-rendered some charts, and I'd like to show you one. You could click on the links, but I've already loaded them in here. So this is a 3D map of actually what's the data. This is from 2005. So I also used KML to just directly plot a three-dimensional image of the measurement. I colored it and triangulated it. So this gives an idea of the area which is measured. And of course, you could load data from several different points. Just click on it, and then you can really make your own map as you go. Another one which is important, I've created this time animation. So all the different data which is stored at this point. Let me just load everything. Might take a sec. Okay, there it's coming. And now you see how the profiles have changed in time. You see in the beginning nothing much changed because it hasn't been measured that frequently. But in the later years, you can see how the coast has changed. So I'll just do it myself. You get a good idea of how the coastal evolution is of this area. Also, you notice, like in the back, in 1980, there's hardly any bumps. It's a very smooth, bathymetric map. But in later years, there's a lot more detail. Of course, the topography probably hasn't changed, but it's more that the measurements have changed. So it's probably multi-beam echo sounder instead of single beam, which gives you more detail. But if you can quickly compare all these maps, then you really easily get an idea of the changes which have occurred in time. Okay, so it's a small wrap-up. If you use Google Earth as a visual front-end for your database, I see him out of the screen.
Just stay seated.
Okay, so if you use Google Earth as a visual front-end of a database, well, first thing is it looks good. Everyone can use it. I just showed you in a live demonstration, which went almost flawless. No, but everyone can use it. Google Earth is a user-friendly program. I think Google put a lot of effort in making it easy for everyone to use. So no complicated menus and nothing, no complicated installation procedures. And good thing, no license fees. It works on a lot of operating systems. You have lots of possibilities. You can make it interactive. You can use 4 dimensions, 3-dimensional plus time. Which is a huge advantage over most other data viewers. So yeah, to wrap it up, Google Earth can be used as a visual front-end for the data in OpenEarth, and I think for many other data sets. Now, one big wish I have for KML is that I could have a user-adjustable DTM so that I could adjust the terrain model without having to make complicated 3D overlays and be able to dig a hole in the earth to show my own data instead of have the data as it is now that have to raise everything up from the earth. Now, OpenEarth tools, everything I've shown here is created with MATLAB. It's a source code, the documentation and tutorials to use this is freely available. So you just go to openearth.eu and you'll find everything there. So thank you for your attention.